Hello everybody, this is Dr. Pennington again. In this video I'd like to talk to you about a particular thermochemical law called Hess's Law. What Hess's Law talks about is the enthalpy change, and we've seen about what enthalpy change means before. The enthalpy change for a particular reaction, as indicated by delta H reaction, is independent of the pathway. In other words, no matter how you get to a particular product, provided you start off with at least vaguely similar starting materials, the overall enthalpy change will be the same. It's kind of like if you imagine going up a steep hill, either walking sideways up it or just going. If you imagine that this is your hill, either you circumvent it to the top like that, or you go around it like that and get to the top. The idea is the amount of energy spent will be the same. Anyway, so it's a little bit about what Hess's Law is all about. We're going to be doing an experiment about this, and I want to talk about it conceptually as well. So on the second slide here, we have an actual Hess's Law sample problem that we're going to work through. I'm going to talk a little bit about conceptually what's actually happening. So the idea for Hess's Law is that you take several reactions and try to combine them in such a way as to make them energetically equal to this one. So this one says find the heat of reaction for this reaction using these three. In other words, add these three together in some way to get this, and then do whatever you have to do with the delta H's to get the overall delta H for that reaction. In terms of the lab, we're looking at an overall reaction of sodium hydroxide, solid sodium hydroxide, plus HCl. Now this won't be a surprise about the products here, sodium chloride and water. This has a particular enthalpy change to it, which we're going to measure. Alright? And the question is, can we figure out another way to make these two products from something similar to these and see if the enthalpy change for however many reactions we have combined, see if those equal this. In order for us to do this, we're going to look at three separate reactions. Alright? Reaction 1, and you guys are going to run each of these in the lab. Reaction 1 is going to be this. Solid sodium hydroxide dissolves in water. Oh, hang on a minute, that shouldn't be in equilibrium, that only goes one way. Solid sodium hydroxide dissolves in water to give aqueous sodium hydroxide. Alright. The water's not shown in the equation here. Actually it is, it's shown by the aqueous designation. This reaction has a particular enthalpy change associated with it. We'll call that delta H1. This we can measure in the lab, or at least we can get the heat exchanged and get our delta H from that. If you remember, we saw in a previous video that to get delta H we get it from the Q value for that reaction. For the second reaction here, we're going to take HCl and aqueous NaOH, not solid but aqueous, react them together and actually get these two products up here, NaCl and H2O. We'll call the enthalpy change for that reaction delta H2. And then the third reaction is this one here that we're trying to figure out. So in this case we've got solid NaOH plus HCl goes to exactly the same products as we've already seen before, plus H2O here. And in fact that should be liquid and that should be liquid. Notice the 2 and 3, although they're very similar, they're not exactly the same. Aqueous NaOH, solid NaOH, and I could have put this NaOH on the left here, it doesn't really matter. The important thing is that the two states are different, so therefore the two reactions are different, so therefore they have different delta H values. Alright? So reaction 3 is our overall reaction, it's this one up here. We're going to measure that value of delta H. then the question is, can we take reactions 1 and 2, somehow add them together to get overall reaction 3? Because if we can we then say that the sum of delta H1 plus delta H2, can we make that equal, or can we show it to be equal to delta H3? Well, maybe. That all depends on whether or not we can take equations 1 and 2 and add them together to get equation 3. Well, just think about it, alright? Equation 3 is the overall equation we're looking for, alright? Somewhere we have to do something with equations 1 and 2 to get to equation 3. And the way we go about this with Hess's law is the same way we've done it with every other time we've added two equations together. When you add two equations together, for example, when we looked at net ionic equations, what was it you did with the species that were present on both sides? Well, as you saw, they cancelled each other out. And it's exactly the same here. So let's see what we have. On the left we've got NaOH, HCl, and NaOH. Alright, but that's solid and that's aqueous, so those won't cancel out, plus they're on the same side anyway. We've got to find one of these three species present on the right. And the only one that is present on the left and on the right is the aqueous NaOH. So if we cancel that out with that, we have NaOH solid plus HCl aqueous, which is what we have here, goes to NaCl aqueous plus H2O liquid, which is what we have here. What we've shown then is, at least in theory, combining equations 1 and 2, we can get to equation 3. So 1 plus 2 in this case equals 3. But is that true for the delta H's? Well, in theory it is, according to Hess's law. The question is, can we experimentally prove that? Well, we're going to try. That's what the Hess's law lab is all about. We aren't going to get the exact numbers because Hess's law requires a perfect insulator when you're doing calorimetry, which we don't have, so we will just do what we can do. And you see, all we did was we just took these two equations and added them together. That's the manipulation that we did. In some cases you might have to multiply this whole equation by 2, this whole equation by 2, divide it by 2, or whatever. The point is, whatever you do to the equation, you do to the delta H. So if we had to multiply this by 2, we multiply the delta H by 2. If we had to flip this whole equation around and put the NaCl and H2O on the left, the HCl and NaOH on the right, we flip the equation, so we flip the delta H as well. In other words, we go from positive to negative, or from negative to positive. Those are the only manipulation things you need to worry about. Now, this is a very simple case of applying Hess's law. Let's look at one in a little bit more detail. Alright, we have exactly the same principle. Oh, sorry, I'm drawing all over here. The question that we're trying to ask is, can we figure out the delta H for this top reaction? The answer is yes, or at least I hope the answer is yes. Can we figure it out using these three? Because each one of these has a delta H value. Well, the answer is yes, we can. We figure out what manipulation we have to do to each of the equations to add them up to get this, and then do the corresponding manipulations with each of these. Alright, so where is a good place to start? Well, the best place to start is to look for the most complex molecule in your overall reaction, and you can argue that's the N2O. The other way to think about it is, look for any one of these three species that's present only in one of these three equations. So, N2O will work fine. Notice the N2O is only present in equation 3. I'm going to say that's delta H1, 2, and 3. Alright? So N2O is on the left, and in the overall reaction it needs to be on the left. So as far as the N2O goes, nothing needs to be flipped. We're not going to worry about the 2 versus 1 yet. We'll worry about the coefficients later on. So what I'm going to do is I'm just going to take equation 3 and write it out again over here. So 2N2O gas. You know what? For some reason I have equilibrium arrows on the brain. I'm sorry, everybody. That should be just going that way. That's going that way. That is going that way. I don't know why I have equilibrium arrows on the brain. Anyway, so 2N2O goes to 2N2 gas plus O2 gas. Now we didn't do anything with that, so we're just going to leave it the way it is. Delta H3 equals 163.2 kilojoules, negative 163.2 kilojoules. Alright, so that's the N2O sorted out. There's a couple of different ways you can do it now. Now we've introduced N2 and O2. Notice O2 is present in both of the other equations, so we're going to leave that one. But N2, however, is present only in one of the other reactions, and it's the second one. Is N2 in the overall reaction? Of course the answer is no, which means we need to cancel it out somehow. If we have N2 on the right in this equation, then the only way to cancel out N2 is to put it on the left in the other equation. So therefore that means we don't need to flip the second one. So I'm just going to write it out as well. As I said, we are not worrying about coefficients right now. Clearly 2 does not cancel out with 1. But I just want to make sure I have everything on the correct side before I start messing about with the numbers. It's a good approach. So delta H2 is, we said that was plus 182.6 kilojoules. Alright. Now for the last one that we've done, we have got rid of the N and 2. Now look at our NO2. We haven't done anything with NO2 yet. NO2 is on the left in the overall reaction. The only reaction that NO2 is in, and the only reaction we haven't used that, is reaction number 1. NO2 on the left, NO2 on the right. We have to flip this reaction to get the NO2 where we want it to be. So when we flip the reaction, we flip this value as well. So therefore, 2NO2 gas goes to 2NO gas plus O2 gas. Alright? And because we flip that, we're going to flip the sign of this as well. So this is going to be positive 113.1 kilojoules. Alright. Now, we have put all the equations in the right order. But we already know that adding these up is not going to get us the right answer, because we already talked about how some of the things don't cancel out. So we have to make sure that they do cancel out. Let's look at the N2s first. I got 2 here and I got 1 here, and I need none over here in the overall reactions. That means I've got to multiply this by 2. But I can't just multiply this by 2. I have to multiply through everything in the whole equation by 2. So therefore 2, 2, and that becomes 4. Which also means I multiply this enthalpy through by 2. Alright. So let's see. Our nitrogens appear to cancel out, so let's cancel those. Do our oxygens cancel out? Because we know we don't want our oxygens to be in the overall reaction. Well, we've got 2 here, so therefore we need 2 on this side, but we only have 1. Oh, hang on, we have 2. So those 2 will cancel out. Alright. This leaves us with N2O, NO2. Both of those are on the left-hand side as we want. And then NO. Alright, which is what we have. We have 4NO here and 2NO here. So when we add all these together, I'm just going to write out what we get. 2N2O gas plus 2NO2 gas goes to 4 plus 2, or 6NO gas. Right? You can clearly see that the number that we have, the numbers that we have here do not match the ones we have in the overall reaction, but they're present in the same ratio, 1 to 1 to 3, 2 to 2 to 6, or 1 to 1 to 3. we're going to add all these up first and then do the last manipulation we have to do. So we've done all our manipulations to our equation, so we're going to do the same thing here. Negative 163.2 plus 2 times this plus this, alright, that gives us, let's see, what does that give us? I guess I better calculate that. Well, we have negative 163.2 and we have 182.6 times 2 plus that plus 113.1 gives us a total of our enthalpy change for 315.1 kilojoules. Alright? But that's not the delta H we want, because this is not the same as this. What do we have to divide through by for this to get to this? Of course, we have to divide through by 2. And if we divide the equation through by 2, we're going to divide this through by 2 as well. And what we get is 157.6 kilojoules. That's the answer. So all we've done is take these 3 equations, manipulate them as we need to, add up all the delta H's after those manipulations, and do any division and multiplication at the end to get from here to our final answer. That is Hess's Law, and hopefully it makes sense about what we're going to be doing in Hess's Law for the lab as well. Alright, that's it. Thank you.